Good afternoon, everybody. My name is Jesus Perez, and I am a mechanical engineering major from Santa Barbara City College. And as Wendy mentioned earlier, I'll be transferring to Cal State LA. So this summer, I've been working with AIM Photonics under faculty advisor John Bowers, and very closely with my mentor Akhilesh Pope. So, with the vast potential in optical circuits due to their larger bandwidths and faster speeds, and with today's growing digital universe, as can be seen here in this graph, it is important to continue research in this field. And AIM Photonics is currently doing this, not just this program, but with all the graduate students here. So, more importantly, this summer I've been focusing on what we call multimode interference waveguides, or MMI waveguides for short. Their main purpose is basically to generate multiple images of an input source, in this case lasers, working in the near-infrared spectrum. In my simulations, I had run at 1.55 micron wavelength. So various components in optical circuits require these images and generation of multiple images to work. For example, optical switches and photodetectors, things like that. So why multimode interference? So as mentioned earlier, in the fabrication processes, we can actually get some variation in dimensions. With multimode interference, they are more robust and actually don't depend so much on, they are less affected by the small, minute changes in the fabrication process when working at such a small scale. I mean, this is in the micro scale, so 1-2 microns in width. Aside from that, they also have low inherent losses when optimized and allow for a potential and very large bandwidths. And they also have a low polarization dependence. Here we can see an optical circuit in which a light splitter or a 1x2 waveguide is being used. So where do we start when we're designing these? There's a lot of math to it. I'm going to run through it fairly quickly. It is not at all. They're not at all dense. So basically, we start with an input field profile at a distance at a propagation distance of 0, seen here. We can then introduce a propagation distance of c, which gives us a superposition of the input field. And then we can actually substitute in our propagation constant, our beta sub m, and then we can go at our physical amount of way out, and we can see that the summation, which corresponds to the images produced, will be dependent on the mode excitation factor and the mode phase factor of this summation. If we look at this more closely and we insert L sub Si for our Z factor, we see that our mode phase factor would be equal to 1, thus giving us our input field varied by the modal excitation factor and shifted by the phase of the lateral plane wave. But basically, we can get an input field and at a certain distance get that same input field propagated through. So if we actually insert 1/4 of this self-imaging distance, here we see that our modal excitation factor is equal to Jn1, and then we can separate these into the even and odd modes, giving us our input field here and actually a mirrored image of the input field. So it's not actually just cutting a light beam in half. We are actually getting a mirrored image of the input field along with the original input field. I have not included the shift in the phase factor here, just for simplicity. But we can actually use this distance here as our distance for, let's say, a 2x2 MMI waveguide, which has 2 inputs, 2 outputs, to get the correct splitting that we require. So if we actually look at this case and we introduce a stepping integer of p that will step through 4 unique self-imaging lengths at quarter distances, we can then simplify this and get an analytical expression for our self-imaging length here. And then we can actually apply this to asymmetric interference, which would be the case of a 1x2 as opposed to the 2x2 that we saw earlier. With this symmetric interference, we see that our self-imaging distance now at a quarter of the distance for a 1x2 as opposed to a 2x2. This is where I actually began to then start designing a 1x2 MMI waveguide model. So here's a side profile of a typical silicon on silicon dioxide waveguide. I will refer to this as my core, and my bird oxide, it will be my cladding. So the first step is calculating the normalized frequency of the specific waveguide that I've been designing. This is dependent on our materials used. In this case, SI for the waveguide, and then SiO2 for the cladding. From here, we can calculate the propagation parameter. Because we're dealing with symmetric interference, we can actually use our result from our normalized frequency to calculate this. And from here, we can get our effective index. And then from there, we get our self-imaging length. And from the previous derivation, we see that the correct length will be equal to 8 times the number of outputs, in this case 2. So from here, I started using a program called Numerical Mode Solutions. This allows me to create virtual models of waveguides. And I start off by getting specified materials for what I'll be using, SiO2 in this case. And I got a model from my mentor, and he told me, okay, you're going to work with this and try to optimize this. So I start analyzing the dimensions given of the input and output waveguides, the specific width. I can then calculate what length I needed. And then from then on, I had various monitors and sources. Here we have an input source, and then we have monitors. And with this program, we can actually run eigenmode expansion simulations as well as finite difference time domain simulations. And here's a perspective view of one of these waveguides. So the next step would be adjusting the output positioning of the waveguide, leaving the input at a center of x equals 0. And from data taken and simulations ran, I see that it has actually a substantial outcome to where the positioning of these outputs are. We had a good increase, although it's still not optimized. What we have here, what we need to account for is something called radiation mode loss, which happens when we have wave propagating from a wider waveguide to a thinner waveguide, or vice versa. The way we do this is by introducing tapered inputs and outputs. So using numerical mode analysis, I ran a parameter sweep of varying widths from 0.4 to 1.1 microns. And we can see here that an increased width decreases the loss. But we are also limited to how much our width of our input and outputs are by the total width of our MMI. So moving on, after using a determined width, I then started adjusting the length of the MMI, of the input and output waveguides and tapers, effectively decreasing the slope with an increase in length. And we can see here that an increase in length also increases the transmission of the MMI. But again, this increases the overall footprint of the waveguide, so we need to have a balance between that. I also, once I set my parameters, I can then run using FDTD simulation. I can run a simulation of an input pulse wave. So here we have our input. Now we have this propagating through, and these are our tapers. And we get two modal splittings, input 1 and output 1 and output 2. So basically for the future, we can use mathematical analysis to have a starting point for our dimensions of MMIs, not just 1x2s, 2x2s, 3x3s, and far more complicated waveguides. And with that, we can introduce these techniques, tapers, different lengths, different dimensions, to increase and optimize these components that are used a lot in these optical circuits, and overall increasing efficiency of our optical circuits. And with that, I would like to thank my mentor, Akhilesh Kope, for all the help. Coming from a mechanical engineering background, this was all very new to me. I had heard of optical fiber before, but never to this scale, or never understood how we could use this. So I've actually learned quite a lot this summer. I also like to thank John Bowers for allowing me to do this and putting all of this together. And then I would like to thank Wendy, and Jens, of course, and Stephanie, and everybody else, all the interns and mentors in the office, just helping me out along the way.